Yeah, good afternoon. Welcome, everyone. Louder? Yeah.
It's not amplified.
But I can speak louder. Yeah, well, good afternoon and welcome to this two-part lecture series on bosonic quantum error correction by Professor Barbara Terhal. Many of us were here in the Central Lecture Theatre a few weeks ago for her colloquium on quantum error correction. I did not want to spend time on elaborate introduction and so on, but I just want to mention that she has been a visiting faculty here for the last almost 3 months now, and it's an absolute honor and pleasure to have her interacting with our groups here. She is, of course, an expert on quantum error correction. Some of us have seen her reviews of modern physics article on quantum error correction and so on, specifically on topological quantum error correcting codes, including surface codes and toric code and so on, and also on this class of so-called bosonic codes. And so today and tomorrow, what Professor Barbara will tell us is about bosonic quantum error correction, which is becoming increasingly relevant and increasingly closer to physical implementation in many systems. So she's also going to tell us about some implementations of these in superconducting quantum circuits. So maybe we welcome her with a round of applause and then we get started.
So I'll spend 3 hours talking a little bit about bosonic quantum error correction. There's a lot of ground to cover, so we can't cover it all. I'll be emphasizing its realization. So I've been writing a lot of reviews. Maybe I should do some original research. But anyhow, so this is a review we wrote in 2020, which is already a little bit outdated, I would say. But it covers some of the basics that I'll also have in this lecture. At least it gives you pointers to different types of bosonic qubits. Now, okay, so what is the goal? What is bosonic quantum error correction? Space is very large, so we can put a qubit in there. Why not use it? And this is in principle hardware efficient because I don't need to control over multiple elements that I have to make, or I don't have to make multiple elements. I have one cavity with some modes, and I pick one of those modes and encode information. So this looks hardware efficient. Now, I think in some sense the jury's still out whether these types of qubits, because in some sense they're just qubit as any other qubit that I can come up with in a quantum dot or a superconducting qubits, whether these are good qubits. Because in the end, any qubit that we can imagine has a finite lifetime, has finite x and z error rates. And we don't expect that this platform will give us error rates that are so low that we never need to use any other codes. And so low, I mean, some people call this algorithmically low error rates, like 10 to minus 18 or something. Like you do a logical gate, you do a gate, and it has error 10 to minus 18, which sounds kind of crazy from a physical perspective. Right? So you can say, well, okay, so what do these bosonic qubits offer more than other qubits, like the transbone qubit that you may have heard about in David's lecture? Well, maybe you can already correct some errors. Maybe they are better than a transbone qubit in some sense of better. Or maybe they have bias noise. Or maybe they're just interesting things to explore because we don't quite know what the future will look like and how we can scale up our engineering and so on. All right, so that's just some side points. Now, okay, so I said we want to encode a qubit in an oscillator, say a harmonic oscillator with some quadratic potential. And, all we learn in undergraduate physics is such a harmonic oscillator. For example, it could be just a particle in a quadratic potential with some mass. And that particle has a momentum and a position. And we'd have a Hamiltonian that we can write like this. And we introduce an annihilation operator, which is a linear combination of the momentum and the position. And then that Hamiltonian has these equally spaced levels, a ground level on the first excited, but the spectrum is completely equally spaced. And in the past, early on, sort of maybe say 20 years ago or maybe 30 years ago, people often said, oh, you know, this kind of spectrum for a qubit is like bad. We don't want to, we want anharmonic oscillators, right? The transmon qubit is an anharmonic oscillator where the second level comes down a little bit. And here we may be, you know, starting with a Hamiltonian, of which these levels are approximately equally spaced. But then the thing is, we say, well, maybe we have, you know, other ways of controlling what goes on in this in this oscillator, and maybe the Hamiltonian is actually a little bit more complicated than this anyhow. All right, but so an good example of such an oscillator could be the motion of a trapped ion. As you've heard the colloquium last week on trapped ion qubits, there they prepare GKP qubits where the ion is used as a normal qubit, and then its motion, the motional mode, is used to encode a GKP qubit, which is an example of a bosonic qubit. All right, now in our setup, so in superconducting qubits, what we will see is that this oscillator is a quantized LC oscillator, or you could say it's just a resonant mode of a resonator. And if you've gone to the lectures of DiVincenzo, again, I'll show a picture. You can have these what we call coplanar resonators on chips, so they're in the plane. But we can also have three-dimensional cavities that, like a microwave. So these are, the point is for this setup, we always talk about microwaves. So your home microwave is an example of a 3D cavity, which is not of high interest for quantum processing, but it has resonant modes for sure. But of course, sort of an abstract picture of a resonator could also be an LC oscillator where we have inductance and a capacitance in parallel. And you'd have a Hamiltonian that kind of looks like this. So you could say, well, you know, there is here I have potential energy goes to kinetic energy, and here I have magnetic energy stored in the inductor goes to electric energy, and this process goes back and forth. All right, so maybe you can ignore what I've written here. The point is to introduce these dimensionless quadrature operators, because those will be coming back often, and if you know some quantum optics, then you've seen these before. Right, so unlike these position and momentum, they're dimensionless. So in this lecture, and in both lectures, I'll be using a lot of quantum optics language. So I don't know, I think many people probably are pretty familiar with that language. So assume that it's, okay, this is not working, sorry. Yeah. All right, so here's some pictures, as also David showed. So this is, for example, a chip actually at Delft. And there are these wiggly lines. These sort of Pac-Man-like structures are actually transmons. And this is quite an old chip. And these wiggly lines are resonators, coplanar resonators. And if you look sort of at detail, there's sort of like, there's a substrate, which is dielectric, and then there are two ground planes, and there's a middle conductor, which is also, you know, the ground and strip are superconducting. And so there could be an AC voltage traveling along this strip. And if you terminate the strip, you know, at the ends, you could have a standing wave, and so you have a resonator. But this was all sort of covered in David's lecture. And so depending on the size of this thing, you know, these resonators can have resonant frequencies, you know, at gigahertz. This is just some estimate. Okay, but now another setup where actually quite a few experiments by the Yale group have been done in this setup is to use 3D cavities. So the 3D cavity, you really have something like a block with this aluminum. There's a hollow in there. This is like some coax cable that goes in there. And this, you know, there can be an electric field in this hollow. And so there's resonant modes that you can address. And you'll see another picture of this as well. And the advantage maybe of these, well, one advantage of such cavity is that usually they have very long lifetimes. So the the Q of the cavity, which is how many cycles you can sort of execute before you lose an excitation, is very, very high. Whereas these coplanar resonators, there's more maybe losses through the dielectric or other things. Although in the second lecture, I'll talk about some recent experiments where they actually use these coplanar resonators to make a cat qubit. Now, I said I was not going to say much about optics. So there's interesting work, for example, by the Furusawa group in Japan and also by the company Xanadu. They want to do optical quantum computing, so very high frequencies. And then it's very nice if you could make a bosonic qubit in a propagating optical mode, because then, you know, you put it through beam splitters or squeezers or something. You have these sort of components. But what is hard about optics is that the interaction, you know, the nonlinearities, interaction with matter is weak compared to circuit QED. So I sometimes call circuit QED sort of quantum optics on steroids, or you know, regular quantum optics on steroids, because we have a very strong nonlinearity, and that allows us to, well, to make qubits and to have, you know, strong coupling in many ways, and this is harder to achieve in optics. All right. Okay, so now I mentioned already the hardware efficiency aspect that is always stressed about bosonic encoding. And this also goes together with sort of, you know, like a statement of the experimentalist that deviates from quantum error correction theory, where, you know, if you have a quantum error correction theory, say, well, I learned I have to correct poly, you know, X and Z errors. That's like, you know, Nielsen-Schwang, the Bible, tells me to correct X and Z errors. But if you're an experimentalist and you just have an oscillator which loses its excitation, say, well, look, my dominant source of noise is photon loss of excitation. So let me just try to design a code that is correcting that primarily. And so that is a little bit the story of the cat codes in some sense. But there is also a caveat to that, in the sense that once you start correcting noise, you inevitably will introduce new types of errors. So maybe you have to couple your pristine, you know, oscillator in your 3D cavity to a transmon qubit. And then this transmon qubit, as you know, it's a nonlinear oscillator. And this nonlinearity is a little bit inherited by the cavity mode. And then that nonlinearity on the cavity mode is actually not wanted, right? So this is the problem of quantum computing in general. Of course, when you open up your system, you introduce errors. So if you have to correct for these errors, you'll be introducing more errors. And the question is, are you going to be on the right side of trouble? Or like, is the trouble, like, are you taking away more errors than you're introducing? All right. Yeah, so here this is a little bit about the Q. This is not so essential for what we're talking about. So, for example, these aluminum cavities at frequencies, gigahertz frequencies, they can have lifetimes to 10 milliseconds and so on, which is still quite a bit larger than the sort of arbitrary or the run-of-the-mill transmon that people make, right? So that people have made transmon qubits up to 1 millisecond. But all right. Okay. So photon loss. Now, I'll be also just, throwing in some math here and there. So, if you want to understand photon loss, you go maybe to QTIP or some other package, but you write down, you could write down a Lindblad equation, and the photon loss, the decay rate is kappa. And if I stuff in, you start with some coherent state. So here's my coherent state. These will be featuring a lot. So if you haven't seen before, look at the formula carefully. Then if I put in a coherent state, this coherent state, if I have this Hamiltonian, which is one of the oscillator, it will start rotating in phase space, and then it will start decaying in amplitude with a rate that's kappa. And here I just wanted to make a little point is that, if you look at the probability to lose one photon in time, delta t, that this increases with the size of the coherent state, right? The bigger the coherent state is, the more rapidly you lose one photon. And this is an issue, or is an issue. It puts a bound on, you know, how high a coherent state we want to make. Because you say, well, I can correct the code in which I can correct one photon loss, but not two photon loss. I should make sure that in, you know, my unit of time that I'm looking, I don't take alpha squared to be too large, such that I lose two. I want to be most likely to lose one photon. Yes?
So assume that kappa has to be positive at all times?
Kappa is a rate, yes.
It has to be positive at all times?
Yeah, well, in this model, I'm just taking a very small, very simple model in which kappa is positive, yeah. So because otherwise this is not a CPT map, yes?
So you have negative probabilities.
Sorry, what?
You will get negative probabilities. P will oscillate between...
Oh, this is just a delta t very short time approximation. It's 1 minus e to the minus kappa t, which is positive, but if I approximate it, 1 minus e to the minus kappa t is like kappa t. So it's just a small, you know, this is an approximate. Yeah, you understand what I mean? I'm just making an approximation that kappa delta t is very small. So I'm approximating what? Yeah, but I'm not talking about that model now. I'm talking just about very simple Markovian noise here. Yeah.
What's the physical intuition behind the photon loss being proportional to alpha squared?
Yeah, well, the point is, of course, that you, well, you can see it in this expression because you say, well, okay, I start, you know, let me square this, right? Absolute value squared. So then you see and this is the number of photons at time t then, is the number of photons at time 0 times some e to the minus kappa t, right? And so if I just take look at the difference being 1, then that, you know, depends on, but it's also like the further out I am in phase space, if something happens with small rate, the bigger the effect can be. Right? I mean, this is true for if I have a rotation in phase space. If I have a coherent state, which is a very large amplitude, I could do a tiny rotation, but then that could still be a big change in phase space because the coherent state is far out. Maybe that's some intuition. Any other questions? Okay. All right. So I'm throwing some other noise models at you, which are not so insightful right now. But then, you know, if you read papers on the subject, then and they're theory papers, or they haven't done the experiment, they basically say, let's throw in these noise models with rates that I may expect, and then see how my code, how my qubit would behave, to get a sense of, you know, what to expect in the experiment. Right? And so I talked also about nonlinearity. So if you remember our transmon qubit, there's also a term like this. You know, sometimes you see it, you can also rewrite it as A dagger A and then squared. You know, there's reasons to rewrite it this way, but this is a nonlinearity, which is also not very nice because, you know, if you see it as A dagger A squared, or, you know, you have to, if you do the commutator with A, you have to pull in the term back to the A dagger A. But you could see this time, you know, A dagger A is like number operator, right? So you could see this as, and if I had, you know, if I had a term which is just proportional to n, this is a rotation in phase space, right? So, you know, the qubit has a resonant frequency, it's rotating. And so you could say, well, this is a rotation that depends on n. But now let's say I have photon loss on my oscillator. So this is only a rough picture. Then my n is actually indeterminate, right? Because the n goes down to n minus 1, but I don't know quite when it happens. Which means that this becomes a dephasing, a source of dephasing, right? Because the speed of rotation, which is just for, you know, if I have omega, and this is like the angular frequency. But for this type of term, the speed of rotation is set by n, but if n becomes indeterminate because I have photon loss, it induces dephasing because I don't know how fast I'm rotating. Right? So this is an effect that, you know, like in Ting was, I think, yeah, the speaker, he was mentioning that dephasing is a bad source of errors, and I was wondering whether this is, you know, well, he doesn't have the nonlinearity, I don't know. So this has been observed as a problem, that the Kerr nonlinearity, which by itself you would say is already trouble, if it's, but maybe it's small, but in the combination with photon loss, it can do bad things. Okay, now of course I can decouple wanted or unwanted with other modes, with a bath or something, and some of the proposals, and we'll discuss this, are also focused on bath engineering. So they engineer the Lindblad equation, which of course is always an imperfect thing, like maybe you have a single photon loss term, but then you want to engineer some kind of 2 photon loss term as well. Okay, but here I'm not doing much with it. Now, and dephasing, you could say that's like, I could model that with a Lindblad equation where I have some dephasing rate, and now this is just some notation I'll be using, but it's also common in the literature, where you have d of a is shorthand for this whole thing, right? But this dephasing could come about like, I put on my frequency of my qubit, I put some sort of Gaussian error, so that it's not that frequency, but it's, you know, it's sampled from some Gaussian distribution with some standard deviation. And actually, if you then look at, well, what kind of noise you get, this dephasing, for that's not a Lindblad equation, but it kind of models this type of thing. All right, so some things, you also have photon gain, and typically, you know, if you have, an oscillator that goes to its thermal state, you'd have, you know, operators like this. But typically the setup, especially for these superconducting qubits, you've heard they are happening in the dilution fridge, and you know, the temperatures are so low, gigahertz, that these qubits, you know, or these resonators, they go to the ground state if you just leave them alone, right? So if you look at the thermal state of a transmon qubit or one of these resonators, it has barely any occupation on the state 1 or 2, given the temperature, which is this millikelvin. There's an exercise in the book that has, yes.
So yeah. There are then 2 sources of dephasing here, one coming from the Kerr term and one...
Yeah, well, of course, I just throw in a few things. I say, well, you know, for example, if you want to model this, and there's, you put in some photon loss, and you also have this, and then that by itself. The point is, okay, the reason I'm throwing this in is that I remember thinking, well, why do I have the phasing? Why is that a natural? It doesn't seem like a very natural noise model, because the frequencies of these oscillators is set by the resonator length. Like, why would it change? Now, okay, so if it's a coplanar resonator, you know, or a transmon qubit, there is frequency fluctuations because it couples to other degrees of, and you don't control, there's 2-level effects and so on. But for like one of these aluminum cavities, it doesn't seem very natural to have any jittering on the frequency. And then I learned that this was because of a combination of the Kerr nonlinearity and photon loss, and that's why I'm pointing out. Yeah. Any other questions?
Do we have any quantum diffusion with losses due to quantum diffusion?
What do you mean by quantum diffusion?
I mean, it's like a kind of transport. It leaks out.
Well, no, okay, I don't really see. So I mean, okay, what it rings a bell to me is that if you describe actually photon loss as an evolution of the Wigner function, it corresponds to drift and diffusion, but that is in phase space. But that's maybe, I don't know whether that's a diffusion you're talking about. There's a way of, actually, I do this in the review because I think it's a nice way of describing things. But, yeah, but the diffusion, I don't know what would be diffusing if I have, yeah. You have, I don't know, if you want to be more specific. Okay. Other questions? Yes.
So the Kerr effect here has to do with like nonlinearity in the dielectric medium?
No, not in the dielectric medium. So where this Kerr effect comes in from, the thing is that, I don't know whether David went in. So for example, I have a transmon qubit. So in order to do something with this mode, I have to couple to it. And I would typically like to couple to it with a qubit. And it typically comes about through some Josephson junction. So I have some, and Josephson junction, as you know, is nonlinear. If I would write it in terms of A daggers and, you know, and so on. So, but then it's very hard to have that nonlinearity only be, you know, sort of on the qubit side and nothing on the resonator side because they're coupled. So typically, you end up with these terms also. And actually, there is a result. So I don't know if David talked to you about black box quantization a little bit. So anyhow, so there is results. So there's a method to quantize these you know, resonators and qubits, these Josephson junctions, and then you get cross Kerr interactions. So for example, so you have two modes, mode A and B. And mode A, you want to be a qubit, and mode B, you want to be bosonic, meaning that mode B should be completely harmonic. You know, that's where I'm going to store my information, and this could be very anharmonic, and I'm going to use this to maybe read out things like that. But I want them to couple, so I want to have this type of interaction. And in this black box, well, this is a paper by Gervin and some other Nig et al. They have, like, for example, observation that if you get this with some strength, you'll also automatically out, and maybe she also already lectured about, so we'll see how. But I think it's instructive to put this in because it gives you a sense of, like, what am I supposed to, what should I expect when I use this code? And then I'll hope to talk about GKP codes. And then the next lecture, we'll talk more about cat codes and so on. All right, so then you say, okay, I have an oscillator. Now, if I have these states with a bar over it, it just means this is my logical zero. This is what I call zero. It has no other meaning than that, right? So I have a code in which I call the vacuum state my logical zero, and the state with a single photon I call my logical one. All right, that's the Fock encoding. Now, okay, so what's good and bad about this choice? Now you say, well, okay, it's very simple. I've used a few photons as possible, so I have photon loss. The long idling time, because this scales with the, you know, the lifetime. This, typically, if they do experiments where they compare another encoding with this encoding, and it's hard to beat this because you only put one photon in. This state stays forever, the vacuum, right? At least if there's photon loss. All right, but why is this not a very good encoding? Can somebody give some, like, why would you not choose this encoding? I mean, I'm just having a harmonic oscillator, chase the two lowest levels, call them 0 and 1. Like, what do I want to do with the qubit? Yes? Right, right. So this is the point. The way we drive an oscillator is through displacements, and we drive it from a vacuum state to actually a coherent state. And maybe you've seen this before. The coherent state is, you know, it's never a Fock state, right? Or it always has a superposition of many states. So, and why do we drive to this coherent state? Because indeed, the transition 1 to 2 has the same energy as the transition 0 to 1. So, you know, if a microwave photons don't care, they only care about the energy they can dump. And they don't care about whether it's between 1 and 2 and 0 and 2, 0 and 1, right? So we drive, if we say, I want to do a qubit rotation in this space, that's hard. Now you say, well, you could say, well, do I really need to do a qubit? Can I come around this? I think these are kind of interesting questions, but you can say, well, how do I measure also this, you know? Now you can say, well, okay, well, I could be, you know, saying whether the parity, I have an even or odd number of photons. That would be a measurement, right? If I could do that measurement, saying number of photons even or odd, I could distinguish 0 and 1. You know, distinguishing 0 plus 1 from 0 minus 1 looks a bit harder to do sort of natively, because then I say, well, yeah, of course, if I could do a rotation, but the problem I can do rotation. So what Atreya was saying is usually the reason why people say, hey, we shouldn't use the harmonic oscillator as to store information, because we can't do these single qubit gates, which just stay us in this, keep us in this two-level subspace. All right, so let's, why is this, it's kind of, this is like this, okay, yeah. Now, this is also extremely simple, and it's surprisingly actually sort of effective in some sense. Okay, so let's take another encoding. We call this the two-legged cat. So now I call 0, I call alpha, and 1 is minus alpha. Those are these two coherent states. Now, so for coherent states, alpha is a complex number. So let me take it to be real, for example. And I have, it is also characterized by a certain number of photons. So if I look for this state and look at the expectation value of, the A dagger A operator, that's the average number of photons. Okay, so anybody, what's good and bad about this choice? You have any thoughts? What could be good? What could be bad?
Not really orthogonal.
Sorry?
Not really orthogonal.
They're not orthogonal in the first place, right? Especially when alpha is very tiny. I'll show you the math equation, but the coherent states are not an orthogonal basis. So, if 0 and 1 aren't even orthogonal, then, that doesn't sound like a very cute qubit. Any other thoughts on this?
Keep moving.
Yeah, but that's okay. They keep moving, so this is the rotating frame. So every qubit I have in the lab is always on the move. Like a qubit on the Bloch sphere, it's also processing around the z-axis. It's just that you need this, you just need to have a clock that's, you keep on, you keep that, right? But this qubit is, it's alpha and minus alpha, and it's just rotating. But as long as we'll see a picture of that. Any other thoughts on what is maybe bad about this choice? We think about photon loss.
Proportional to n.
Yeah. Yes. Right. Yeah. Okay. Let me just go there. Okay. So. Indeed, as was said, these states are not even orthogonal. If you wanted, just the math, if you look at the inner product of two states, beta and alpha, it does decay exponentially in alpha and beta, but, it's not 0. But you can actually make two orthogonal states. You can get rid of it. And this is why this cat, so actually you can just focus on these two states. Let me call this plus, and let me call this minus. And note these states have a slightly different normalization. And but if alpha is very large, then this second term, is 0. So the normalization is just the same. And this is just the Schrödinger-cat state. And this is also a Schrödinger-cat state with a minus. And, these states are why this code, or this cat code, why this is a cat code, Schrödinger cat code, and why it's two-legged, because in, these plus and minus are, superposition of alpha and minus alpha. All right, but now, okay, so now you can say, well, why are these orthogonal? Well, okay, so two things. You can just do the math. And you just have to work out, the things, and there's a minus sign, and it works out. It works out. And then, if you have plus and minus, you take linear combination of those. Those will be 0 and 1, but because these normalizations are different, it will not be quite alpha and minus alpha. Yeah, but okay, close. Okay, so for practical purposes, we can keep that in mind. But these states have also nice features with respect to photon parity that we'll talk about in a moment. Okay, but now the other point that was made, what about that photon loss, right? We cared, of course, you could say, well, we want to do gates, but we also cared about something that is kind of good for photon loss. Right, okay, I apply A on this state. And the state alpha is an eigenstate of A. It puts back, so A on alpha is alpha, or is alpha times alpha. Just write it down. Okay, this is something you can verify. And therefore, if I apply this on plus, this plus sign here, because there's overall alpha I can push out, but this plus sign will flip to a minus sign. Right? So photon loss immediately has a logical action. It puts plus into minus. And then we also said that this, this single, so we want to say, what we'd like is, we'd like to say, maybe there's one photon loss, but, what will happen basically, we can also say, well, we look at alpha and minus alpha, and if there's one photon loss, of course, that single photon loss rate is now the phase flip rate, right? Because it maps plus onto minus. And that has an error rate that scales with kappa times the number of photons. So this is important, right? So this looks like a very bad qubit because if I lose a photon, and the point is, I'll show you that in a moment. This is a state with even photon parity. This is a state with odd photon parity. So I go from even photon parity to odd photon parity by photon loss, right? And so you could say, okay, what is the, and that induces a phase flip error. So what's the probability for a phase flip error? How does that scale? That will scale times kappa times number of photons. So this is a very important point if you want to understand this, the next lecture also, that if we make alpha too large, then we increase our phase flip error rate. Okay, but now the idea, and this is not so clear, you say, well, but bit flip errors, what are bit flip errors? That would be a rotation, say, from alpha to minus alpha in phase space. That's a big excursion in phase space. So you'd say, well, if there's noise, that wouldn't do that naturally. Sort of. But then we'll come later to explicit mechanism that tries to suppress this sort of effect. Like if you move away a little bit from alpha, you're sort of pushed back to alpha. This goes by these dissipative engineering mechanisms. Okay, so the point of this is that this cat qubit may be a qubit that has a noise bias, because if we have a qubit, we like it to be have a low X and Z error rate, and we like to be able to do gates and measurement and everything. But in order to be a good qubit, we say, well, usually we say it has a T1 of this and a T2 of that, and those are sort of placeholders for X and Z error rates. Now, these qubits don't necessarily have a T1 and T2, but you can say it has a bit flip and a phase flip error rate. And so this phase flip error rate gets worse if alpha is larger, but you expect this bit flip error rate to get smaller if alpha is larger. And not just linearly in alpha, but something that is exponential in alpha. But okay, we'll come to this. All right, but now, of course, if we just leave this qubit alone, then with photon loss, more photons will be lost, and it will go to the vacuum state, right? So if we want to encode this qubit and keep it alive, we want to be able to, we should be sort of actively supplying energy. Now, you could say that about any qubit. If you leave a transnormal qubit alone, it also fall to zero. And usually, we don't really have a dissipation mechanism that sort of stabilizes this, because we say, well, whatever errors happen, we do error correction, we have multiple qubits, etc. Right? We sort of bypass that stage. And here we're trying to sort of, because these states maybe that we come up with are sort of, well, we try to sort of do error correction already on this one qubit. All right, now here a little bit about just some background, just about this cat qubit. If you haven't seen it before, or you just haven't seen Schrödinger cat state before, this was also in the colloquium that we heard before. So sometimes it'll be showing Wigner functions, actually not that much, but if you have a density matrix in quantum optics, it is equivalent to a quasi-probability function in phase space. Right, so if I have a classical system, I have a position and a momentum, then I can say, well, I can describe some stochastic movement of the particle by changes in this probability distribution over this phase space. But for quantum systems, Wigner has come up with something that's a quasi-probability, so it can be negative. And you can get it from rho by a transformation. And it's a one-to-one, so it characterizes all. And if you look at the reduced sort of state, so I trace out over the p coordinate or the x coordinate, I do get probability distributions. Right? And so coherent, and so these are often used to just sort of, plot what happens. Right? So you can start with a coherent state Wigner function. And if you apply photon loss, you'll just go to the vacuum state and it will be a Gaussian blob around the vacuum. And so the Python this software is, I think, quite useful with all these tools. Okay, so now just if this animation is working, this was actually just from Wikipedia, but it's just for the, right. So if I just have a cat, alpha plus minus alpha, and like I said, it's rotating. So this is in phase space, and this is the Wigner function. The problem, so there are these interference fringes in the middle, and these are different from the alpha plus alpha than the alpha minus alpha. But the problem is that if I flip randomly between alpha plus alpha or alpha minus alpha, of course I will lose this. I will lose this interference fringes. And Harosh, who passed atoms through microwave cavities, so not anything superconducting, he got, he shared the Nobel Prize with Vineland for this kind of work to create cat states in these microwave cavities manipulated by these atoms that were passing through. Yeah, and here you see the sort of the reduced density matrices, or the reduced probability distributions. All right, now I made a comment about photon parity, and this is an important operator because it will come back a few times. So the claim is, and we'll just, we'll do this little thing. So the claim is that these two states, alpha plus minus alpha and alpha minus minus alpha, independent of whether, what alpha is, that they're even for the plus and odd for the minus in terms of photon number parity. So the Schrödinger cat with the plus is a superposition of 0, 2, 4, 8, whatever photons. Okay? And the other one is superposition of 1, 3, blah, blah, blah photons. Okay, but so you can say, well, what's the photon number parity operator? Well, that's very clear. It's this guy, right? Because if the photon number, which is A dagger A, is even, then this has eigenvalue 1. If the photon number has eigenvalue is odd, then this is EDI pi, and it's -1. So this is a nice operator, which actually will also function as a stabilizer, because for example, if I have a code where I'm in an eigenstate of this, then I could be measuring this. But this will come later. But okay, but I can indeed try to measure this operator. Okay, first I want to also verify that this claim is true. They're even and odd in terms of photon number parity. Now, P on alpha is minus alpha. So how does this come about? It's actually a very simple exercise. I put the e to the I, P, A dagger A in here. And I let it act, so this is my coherent state, I just let it act on this Fock state. And it just picks up a phase e to the I pi n, right? So e to the I pi A dagger A on n is e to the I pi n. And this phase factor I can just absorb or join, and that this of course I can put it in here, and then I get yeah, I just put it alpha e to the I pi, and that is minus alpha. So okay, so if we agree with that, then I can apply it to this. And of course, if I apply P on alpha plus minus alpha, they stay roll, but the state stays the same. And if I apply it to alpha minus alpha, they get an overall minus sign. Yeah, so that's why the one with the minus is an odd state, it has odd photon parity. Everybody okay with this? Okay, so now how do I measure? So I can ask, how do I measure any operator which actually has eigenvalues +1 or -1? This is often done for stabilizers, because we just have some string of polys that we want to measure. And we always do this. We take a qubit, we put it in a plus state. So that's my Hadamard, put it in a plus state. Then I do controlled that operator. For stabilizer, this is controlled some string of Pauli's. And here it's controlled P. So what I need something where, depending on the state of my qubit, depending on the state of my qubit, I need to do a rotation. Either the I pi A dagger A is a rotation in phase space by angle pi. Right? So that's what and then I could measure my qubit again in the X basis, because I do another Hadamard. And then the claim is that, you know, whatever I measure here is 0 or 1, that it corresponds to the eigenvalue of P. Right? So if it's 0, then I'm in a plus, and if it's -1, I'm in a minus, and if I were in a superposition, I'll be collapsing the state into these two cases. Okay, this is something, if you want to know more, you could just verify yourself by just sort of, you know, doing the math. All right, now, so this is a very easy thing to do in the setup. Why is it an easy thing to do? Because remember, or if you were at the DiVincenzo lectures, what we have, if we have a transmon qubit coupled to a cavity mode, we have typically a Jaynes-Cummings interaction, right? Jaynes-Cummings interaction is just, you know, just an energy exchange thing. But if this qubit has quite a different frequency as the cavity, we have something called the dispersive interaction. And it's of this form. Chi is the dispersive shift, Z is the Pauli Z of my qubit, and A dagger A is the operators and the number operator for my cavity. And this type of interaction is used to measure a qubit. So, you know, if you have a transmon qubit, I think probably David told you, then there is a readout resonator that is dispersively coupled via this interaction. So what it means is that the qubit changes the resonant frequency of the cavity, and therefore if you probe the cavity, you get a different response depending on the qubit, and that's how you measure the qubit. Here we say that cavity is now not just a readout, sloppy, you know, cavity. Now it's my storage cavity. I have to, you know, everything that's in there should stay in there, and I want to use my qubit to manipulate the state. So I want to do this type of interaction for some specific time such that I have this, you know, this is pi over 2. Why is it pi over 2 and not pi? Is because Z, you know, it goes one way and the other way. Is this clear to everybody? Yes.
It's not conventional stabilizer in the sense that both code words are not +1 eigenstate.
Yeah, exactly. I'll come to that because there's the four-legged cat. So here I'm not doing the stabilizer yet. I'm just saying if I were to do this measurement, I could prepare this state or that state depending the outcome. Yeah. So that's a tool that I can use, but it's not a stabilizer because the two states, these two sort of code words, are one is a -1 eigenstate, the other one is a +1 eigenstate. For stabilizer error correction, usually all the code words are +1 eigenstates. Right? Any other points or questions? Okay. Now, so that was so like I said, in the Yale group, they did you know, many experiments on 3D cavities where, okay, so here this first hole is the readout cavity, and then in between there is a structure which is a transmon. It's like a little antenna sticking out in both cavities because it has to couple to it. And then the third one is the storage cavity. And you know, they can, I mean, here are just some parameters of a fairly old experiment where you say, okay, I have a high Q cavity, is 1 millisecond lifetime. I have a transmon. Well, 10 microsecond lifetime is not actually that high. Then I have some dispersive. I want to have a fairly strong dispersive qubit cavity coupling, which is, for example, 2.5 megahertz. You notice this is, you know, a factor 1,000 less than the frequency at which, the gigahertz frequency at which things are rotated. But the point is, and I think I made this here, actually when you have this dispersive coupling, you also get some nonlinearity on the cavity, which is not so ideal. All right, but they can make these kind of odd cat state, even cat state. Okay, so that's in principle something you can use. But the cat qubit, as we said, has also this, it has this maybe potentially biased noise, but the sort of the Q. So for that reason, in Yale at least, they looked at the different code, which is the four-legged cat, and all these codes. Actually, but I'm not going to talk about baby binomial first. So all these codes are babies, are the smallest ones in some whole large family that is very fun to study if you're a theorist, but maybe you're never going to use to experiment. Okay, but this code, this baby binomial code, has also been studied. And it's a nice code to actually talk about the quantum error correction conditions. Okay, so for the baby binomial or kitten code, what we do is one state is just Fock state with 2 photons. And the other one is the superposition of 0 and 4 photons. So you see the average number of photons in these states is the same. All right, now we're going to, so I want to talk about the quantum error correction conditions a little bit, because you say, well, okay, this looks good. Because maybe what happens if I have 1 photon loss, let's say there's photon loss here, it goes to state 1. Yeah, that's unlike here, right? Here, if I have a photon loss, this goes to the state 3. These are still orthogonal, so I can undo it. I'm done. I'm going to do the experiment, right? So what the point I want to make is that it may be nicer to look at the quantum error correction a little bit more in detail to understand better what's happening. Okay, I'm interested in correcting photon loss. Now, what are the quantum error correction conditions? So this is always a little bit densely written because we have to sort of unpack these. So you start with a set of errors. And for example, I have a silly set of errors, somewhat silly, which is identity, no error, or A, which is photon loss. Note there's no rates in this picture, but there's no A squared, right? So I don't look at 2 photon loss. If I were a little bit more carefully, I'd say, well, for a short time, I could model the photon loss channel by something like this, where I have either photon loss, with some rate gamma, and gamma is like kappa times delta t, or I have no photon loss, and then I actually have something like this. So I also, in order for this to be a valid map, I actually have to add something like this. And so then these 2 operators will act as some TPC map for a short time. All right, so I could either be looking at this, or it could be the modification, but maybe I'll start with that. Okay, so what are the quantum error correction conditions? One is so let's unpack these. So I have 2 code words, 0 and 1. Now, this is labeled by Z, and there's some conditions. So here, these E's are everything I have here, but I just have 2 silly things. So what it says that if Z is not equal to Z prime, and I put errors on both, then they should stay orthogonal, right? And that's kind of what I intuitively already said. Like 2 goes to 1, and 1 goes to 3. So yeah, okay, stay orthogonal, looks good. Okay, so that's this delta function here, right? If Z is unequal to Z prime, I get a delta function. So that's the first thing. Orthogonal code words stay orthogonal due to any of the possible errors that can happen. And I mean, the point of looking at the quantum error correction conditions, maybe to stress that a little bit, is that then there exists an approximate recovery. So the point is that it's like something that is a sort of a necessary condition, but it doesn't mean that you can actually efficiently recover on a physical device, of course. It's just a different thing. Okay, but there's another thing, and this is less intuitive. It also says that if Z is equal to Z prime, so now I just take some expectation value of this product of these errors, then what is on the right-hand side does not depend on Z. So if I take Z equals 0 or Z equals 1, it should give me the same thing. And that is less intuitive to understand, but it's sort of a no distortion type condition. Now here, if you want to know more about binomial codes, I would look at, the quantum error correction zoo. All right, so now what we want to do is say, okay, take these errors, and I'm going to look at the quantum error correction conditions for this baby binomial code, right? So I'm going to check these combinations. And I check whether they all are obeyed. Now, I did this on a piece of paper, so I'm just showing you. Okay, so these are the 2 states. Now, of course, if I have, I had only one operator was the identity, the other one was A, so let me take all the combinations where I only take identity and A, then I get things like this, oh, that's obvious. If I start with 0 and I have a photon loss, of course, it's going to be 0 because it maps to an orthogonal space, right? If I have 1, I have a photon loss. It also maps to orthogonal states. So this is both 0, good, because it should be the same. These things are also good because I have 1, I have photon loss. I map 4 to 3, and that's orthogonal to 2. So okay, fine. And this is the ones in which I take, both of these operators to be a dagger, and I have to base something like this. And this, if you look at this is like the average photon number is the same. And this is, this is z is unequal to z prime. And this is both orthogonal loss, and then they're mapped onto orthogonal spaces. So everything you can intuitively understand is also there, but sort of more in some things that maybe are not as natural to say in words. Okay, but now you can also say, hey, but if I take that error set, it was a simplification of this. There was this little thing. And actually, this E0 leads to distortion. So if E0 is an impossible error and E1, and I don't know which one happens, then if I look at this condition, E0 dagger E0, so this should be the same for 1. That was the no distortion condition, right? But if I plug that in, I get a term that scales like gamma squared, and it looks like kind of like I take the expectation value of the number operator squared, which is different for these states because this is an eigenstate of the number operator and this is not an eigenstate, right? On average, n is the same, but there are different fluctuations. Okay, so this is just a little exercise to show that for some of these codes, sometimes it's nice to look at the error correction conditions. Is there any question here? Maybe this is a little bit too detailed. Yeah.
Small question.
Yes.
So the trivial error is supposed to be I, but we are modeling it as I minus the gamma extra term. Then
well, the error.
The E dagger E condition.
Well, the point is, the point is, if it's the identity, these are not the Krauss operators of a completely positive map. So if the photon if there's no photon loss, there is an effect on the state. This is also very nicely described in a book by Harosh, actually. Sort of, you say, well, there's no photon loss, nothing happens. But actually, there is an effect on the state. Because you're conditioning on knowing that there's no photon loss. Okay, and so this is a better representation. But again, this is approximation for a short time. So it's, it's not even very... Any other questions? Yeah.
Is there some way where you can construct logical qubits in an iterative manner where you order by order and impose these conditions so that you get a better and better logical representation?
Yeah, well, I think in some sense that there are generalizations of these codes, like the binomial codes, which can correct multiple losses. Then, so in that sense, they are things that are. Well, iteratively, it's not like numerically, but there are higher order losses can be corrected. But then you need a higher photon number as well. Yeah.
So you mentioned a short time in your previous slide.
Yeah.
That is time comparable to the gate operation?
Well, yeah, time, what is time? So, of course, you say, well, I want to run a quantum error correction. I want to... Maybe photon loss happens, and then I want to measure something so I can correct it. But then it depends on how long that takes. That I, how long I can wait, right? So the point that time is, for example, so we'll see in a moment that for one other code, we measure through a transmon qubit. The transmon qubit measurement time takes 500 nanoseconds or something. Sometimes longer, 1 microsecond. During that time, there is photon loss happening on the resonator. And that is then a time of which you say, I want at most 1 photon loss to be happening. Otherwise, yeah. Right? So it's typically measurement time that is the most sort of constraining in these things. But not always, but yeah. Okay. How am I doing on time, actually, Barbara?
Another half an hour.
Okay, yeah. All right, so now it's time for the four-legged cat code, because this is one of the first papers, I think, in 2016, it was, well, you see, extending the lifetime of a quantum bit with error correction and superconducting qubits. So they say, oh, we could do a simple FARC encoding on my 3D, 3D cavity, but I can also instead try to preserve these states. Say I prepare this state or superposition thereof, and I preserve it. And what will its lifetime do? So do I extend its lifetime? Now, of course, this has a caveat because you say, well, yeah, okay, now I have a qubit that lives longer, but if the gates that I have to do on it also takes 10 times longer, then I haven't gained anything, right? There's always this, a lot of things have to come together for this to go well. Okay, so plus and minus, so this is four-legged because now I have blobs in phase space, alpha, minus alpha, I alpha, and minus I alpha. And these all come with a plus sign for the plus, and these I alpha minus I alpha comes with a minus sign for the minus. But of course I can take a superposition of these, and assuming now n plus is about n minus, then I get a 0 and a 1, which are my Schrödinger cats. So 0 is approximately alpha plus minus alpha, and 1 is I alpha plus minus alpha, right? So if I want to prepare my 0, I could be, or my 1, I could be doing that controlled P measurement that I just talked about before, right? But now we want to understand why this is a better choice when it comes down to photon loss. And the simple way to understand it is that these two states, okay, let me say it and then we can argue it very simply. So the plus state actually now has photon number 0 mod 4. So it's a superposition of states with 0, 4, 8, etc. photons. And the 1 has photon number 2 mod 4. Oh, sorry, this should be minus, sorry. Minus has photon number 2 mod 4. Right, so if I now lose a photon from both, I'm still in orthogonal states. But okay, so how can we see this? Now, okay, so first of all, it's clear, maybe we should first say this, we've discussed this photon parity operator, which has eigenvalue 1 if you have even photon parity, which is true now both for plus and minus, right? This should be a minus, right? So now this photon parity operator is like a stabilizer, and I could be measuring it to detect for errors. And this is exactly what they're doing. They're just keep on measuring P via a transmon and then controlled P measure, etc. And when they're fast enough, there's only maybe one photon loss in between their measurements, and they detect this. All right, so now, but you can say, okay, but what about why is this the case, this plus and minus? So I call this a plus and I call this a minus, and the poly x I claim is the square root of P, right? It's either the I, A dagger A, but now P over 2. And what does x do on plus? It should return plus, and x on minus should return minus. That's the thing I have to verify, right? And it also says that, this operator, if I look at what is this operator, if this has eigenvalue 1, then n needs to be, something like 4, 8, needs to be 0 mod 4, right? Because this phase has to be either the I2 pi. And if, n is, if photon number is 2 mod 4, then this phase is minus 1. So this all sort of comes together. Okay, so we have to check. We can verify that if I apply this operator now onto these states. Now before you saw that P, we had P, which was a rotation, would go to minus alpha, a rotation by pi, and maybe not surprisingly, I have P is now I alpha. So now it's just from alpha to I alpha. It's a pi over 2 rotation. And if I do that, so I do this, square root of P. Yeah, this is square root of P. This is what I call my logical x. Square root of P does this pi over 2 rotation. And so let's verify, for example, for here, if I do, of course, do this pi over 2 rotation, this state is invariant. And if I do this here, these I alpha thingies go to the alpha thingies and back, and so I get to pick up the minus sign. Yeah, so here we've seen that the photon, they're distinguished by photon number parity mod 4, and they're both eigenstate of this guy then. All right, so this result, so in this paper in 2016, they found that this lifetime of this quantum bit was 1.1 times longer than a Fock encoding, and they used an average number of photon was about 2. And they used this photon parity repeatedly using ancilla transmon qubit, and they really used that information to stabilize the qubit. And maybe I think that is, okay, now I was actually, okay, maybe I'm going to skip. So you can also check, okay, so now we said we have a new code, this 4-legged cat code, and we can now actually, we can verify again the quantum error correction conditions. It turns out that actually these are only fulfilled at some very special sweet spot. I'm going to skip over this because this is just a math cohesion. But it looks like it's not like the cat code where we certainly could not meet the quantum error correction conditions. All right, so here is, for example, some data. I just want to. Sometimes I'm not doing these experiments, but it's still interesting to see what they actually get. I mean, I like this kind of thing. So, so here on the top, the number of cat code syndrome measurements. So what they measure is this P, not the Pauli, so this photon parity operator. And they do this once. I don't know why they have, there's 2 ones here actually. So do it 6 times. Here's actual time, physical time. So you can see how long this happens. And then there's some fidelity. So they prepare states like the plus, the minus, the 0, the 1, the +1 eigenstate of y. See, they're the cardinal states on the Bloch sphere. Here you see sort of a Bloch sphere. And then you can look at what happens. Now, if you look at, so they couple to a transmon qubit. So this transmon qubit, if you put it in 1, it will decay with a time constant which is about 17 microseconds. If you put an uncorrected Fock encoding, which is somewhere over here, so that's just Fock state 1. Of course, if you have 0, it doesn't do anything. If it's 1, then it sort of decays. You can also do an uncorrected cat code where you say, oh, well, I'm measuring all this stuff, but I'm not actually, well, actually, I'm not so sure whether they even measure or they just let it sort of, let it fall, right? You could do 2 things. I could not measure at all, just let photon loss happen and see at the end, how I identify the states. If I measure the parity, say, I could just measure this parity end, say, is it a 0 or is it a 1? But they could also measure it and just throw away that data. And the corrected cat code goes sort of over here. And then the corrected code get with post-selection where they only, if they don't detect the photon, they just keep the data, right? So there's sort of tricks you can play, which is not scalable. All right, so the point is they do some comparison, they see an improvement. But then this is an important point I want to make because it comes up also in a paper that appeared like 2 months ago, which is, okay, so first of all, there are, of course, a lot of sources of errors. There are 2 photon errors in your interval that you couldn't correct. The transfer measurement is not perfect. There is effects of self-Kerr and cross-Kerr interactions, so self-Kerr and cross-Kerr on the thing. Then there is this thing, photon loss plus Kerr can infuse dephasing. And then, this is an important thing, feedback errors. So the question is, and there's no theoretical answer, is your bosonic qubit sort of always bounded by like the bad transmon you couple to it? You say, well, other groups are doing transmon qubits. Why would you be doing something else? Because if you do use this transmon qubit still your setup, maybe its errors will, spoil your setup. So that's a bit the question. How can you get yourself into better qubits? And in this protocol, it was definitely true that this transmon, which had a very short decay. So the point is you have to put this transmon in this superposition of 0 and 1, right? To do this controlled rotation. Now let's say halfway to this controlled rotation. So if it's 0, it rotates this way. If it's 1, it rotates that way. But halfway through this controlled rotation, it falls from 1 to 0. So then it could be sort of doing half the controlled rotation. So instead of doing controlled P, it could be doing controlled square root of P. Okay, well, that's a very special thing. But, roughly like this. And square root of P was illogical, right? So the point is that your transmon actually leads to extra errors, extra rotations that can, that can be a problem. And this is again, for example, in the paper that I'll be talking about tomorrow, where the Amazon group uses the cat qubits, which is not this four-legged cat, but this biased noise cat. They measure properties of it through a transmon qubit. And again, there, the transmon qubit is much better than this. But it again is, a point where errors enter your bosonic qubit. All right. Okay, so now I wanted to, let's have, maybe, are there some questions here? No, so I haven't discussed for this four-legged qubit, I haven't discussed gates and so on. And there's also many papers written about that. Yeah.
So I wanted to get an idea about the time scales here. So you're saying you wanted to measure at a rate that's much faster than the photon loss.
Yeah.
So here the measurement is happening approximately every 20 microseconds.
Yeah, this is actually, indeed this is, well, okay, so they could be, in this setup, they actually don't measure that often. They could be measuring more often. So actually the protocol to do this control P takes about one microsecond, or one, maximum 2 microseconds. But in this setup, they don't do this very often because they say, well, if I don't expect there's photon loss, why would I be messing up my bosonic qubit by some measurement that I know what the outcome is supposed to be, right? So you can adapt. You can say I do it less frequently because I want the probability to be, to have one photon loss to be sizable, but not too large that I lose 2 photons, of course. Yeah, so they kind of balance that. Yeah.
Sure.
Yeah.
Usually, what is the time scale for photon loss?
Well, you can see it from this Fock encoding actually, because this is actually what is it, the uncorrected thing, which is over here. So this is 280 microseconds. So it would be almost a millisecond. I honestly, I don't quite know whether this number is an average of 0 and 1, or whether it's just the decay rate of 1. Yeah, but okay, so maybe I should be careful, right? Because this is for a Fock, this is the decay rate. But like I said, if I have a big coherent state, it gets multiplied by how many photons I have. Here I only have 1 photon, so. Right, and well, I don't have a big coherent state. I have a coherent state with alpha squared is 2, so that's why they can't go to a higher alpha also. Yeah?
Just to understand that setup, so the transmon is there in the system both to prepare your states as well as to read out the parity.
Yes, exactly, yes.
And so to read out the transmon, there should be another readout resonance.
Exactly, yes, indeed. And this is what's shown indeed in this. Well, well, you can't see the transmon actually. These are the 2 resonators, and the transmon is sort of in between there. Yeah, yeah.
So what exactly is the storage, bosonic oscillator we're using?
The storage cavity is where you want to put your bosonic qubit.
So physically, is it the transmon or is it the oscillator?
No, the storage cavity is a cavity mode. It's a cavity mode in a cavity, right? So it's not the whole cavity. It's just, of course, it's a mode in a cavity, but that's how they call it. Yeah. And then there's the readout resonator, or the readout cavity, which is used to read out the qubit. Yeah. Yeah.
There was one slide in which there was a time scale 1.1 times longer or something.
Yes. Yeah. That is based on this estimate. Yeah.
Yeah. So I just.
Yeah, that is.
What's the big deal about 1.1?
Yeah, that's not a lot, right? But this was like the first experiment where they went beyond break even, and then I think then they went to GKP codes, and the last results were stronger than that, but that was sort of the first time, yeah. Yeah, of course, it's all, yeah.
We talked about how root P acts like a logical X gate.
Mm-hmm.
Does this encoding permit other kinds of gates?
Yes, and I'll be talking more about that. See, I don't remember exactly for the 2-qubit gates and so on, and I think I'll be talking more about that when I talk about the noise biased, the cat code. So maybe I'll leave it for that. Yeah. Yeah. Okay. Sure. Okay. Right. So we'll make a start. So how we're doing on time?
Another 10 minutes or so because we started 10 minutes late.
Yeah. Okay. Yeah. I hope not everybody's worn out. Okay. So I'll just make a start on the GKP code. I probably have to see tomorrow. I'm gonna, because I have a lot of material here, and then I never get to the latest experimental data, which is kind of nice to learn about. At least I think it's interesting to learn about. Okay. So the GKP code is also what you heard in the colloquium last week. And maybe I want to make this point a bit more clear, maybe. So, okay, so we have an oscillator, and we're just going to pick a two-dimensional space where we want to put our information. And there's this beautiful thing that I can make two commuting operators that involve QMP. So QMP, I have a commutator that's non-zero, but it is proportional to identity. Then I can make this operator SP and SQ, and it turns out these commuting. Now, I think it's very important if you ever work to this, you just have to understand why this is commuting. Now, okay, so if I have two operators, e to the A and e to the B, of course I can do some kind of Baker-Campbell-Hausdorff, which is it's equal to e to the A plus B plus the commutator of A and B divided by 2 plus A with that commutator, etc. Now, because the commutator of A and B is proportional to identity, all these higher order commutators are out, right? So I only have the commutator of A and B, and that's proportional to the identity. And so with that, well, okay, so with some, but you can also do the same for e to the B and e to the A, and then with some math you can see, you can convince yourself of this relation. And now, so then you say, oh, so that means that e to the A commutes with e to the B when e to the commutator of A and B is a phase that's equal to 1. That's the whole point. Okay, so let me take SP and SQ now. So the commutator of Q and P is proportional to I. So if I look at my A and B and I put in A and B, which are these guys, okay, I get an I squared, I get a 4, I get a pi, I get the commutator of P and Q. So I squared, 4 pi, commutator of P and Q. Here's the -1. Okay, I get e to the I, 4 pi. Good, it's 1. All right. You see, it's a 4. I say, wait, why 2 would be sufficient, right? So it means I can actually take the square root of one of these operators, and it would still commute with these two guys, right? Because then the phase is, and that will be a logical operator. So these will be stabilizers. So, but the point is that because they're commuting, and they're just displacements, they're the examples of displacements, right? With a particular alpha. And so I can say I'm going to make pick a +1 eigenstate of these two commuting operators. Okay, let me imagine what that means. Okay, if this is a unitary, its eigenvalue has to be +1. So it means that this has to be a phase, which is 0 mod 2 pi for every value of that p, which means that p needs to be 0 mod square root of pi, right? Because then if I multiply with the square root of pi, then I get 2 pi here. And the same for q. If this has to have eigenvalue 1, that means that q is 0 mod square root of pi. This is just math, right? I'm not talking how we do this physically. Because p eigenstates, that are actually sharp, and p and q, they don't exist physically. But it just says that if I want to define formally an eigenstate of these two operators, it will be a state for which p is fixed, p is entirely fixed and q is entirely fixed, perfectly. And this is what the speaker of last week was referring to as these are modular quadratures. I'm not fixing p to a particular value because I can't do that simultaneously with q because of Heisenberg uncertainty, but I can fix p and q if I just only care about them, them fixing them modular or something. So a state that has this property will have delta function peaks at these p's and q's, right? But it will not be just one peak, because that's not possible. All right, so that's a neat idea. And actually, my last slide in this set of things, but maybe I'll throw it in, that so Jonathan Holm wrote a paper, I think last year, and he said, hey, if you try to prepare states which have this modular structure, this is a good way of cooling. So you want to cool an oscillator, mechanical oscillator, very hard to cool to the ground state. And he said, maybe, you know, if you interacted the way we try to interact with the oscillator, we're trying to create these states. But this is also a way of cooling. And maybe it's a way of cooling that's actually better than what people do. So I thought this kind of a fascinating idea. So of course you need some more control, because you need a qubit. And okay, so you need some other things that we'll talk about. Okay, so is that clear at this point? Because this is an important aspect. And that's how it escapes, you know, Heisenberg uncertainty in some sense. All right, so now, why did we choose SP and SQ in this way? Because we want them to commute, but we also want there to be sort of room for a logical Z and X. So we just take Z to be the square root of SQ, and we take X to be the square root of SP, right? Which is now we drop this factor of 2. And therefore, these logic operator, so we're going to put our information in the +1 eigenspace as we do with stabilizer code. And these are displacements that do logical Z and X in principle. Right? And you can say, okay, when I'm Z means, you know, 0 should be the +1 eigenstate of Z. So if I'm the +1 eigenstate, that means that Q has to be an even multiple of 2 times the square root of pi. Right? With the same reasoning as we did before, because now I have this. And 1 has to be a -1 eigenstate. So Q has to be as a wave. I could look at these states as a wave function in Q. 1 has to support at Q being an odd multiple of square root of pi. So because then this one has -1 eigenvalue. So that's sort of the picture. There will be 2 states, 0 and 1, and they both have support only at multiples of square root of 2 times square root of pi. And 1 is, you know, focused on the evens, and the other one is focused on the odds. So then you say, oh, okay, so what we need to do is we need to measure the eigenvalues of these stabilizers to learn about the errors. Now, the first thing you have to realize, this is not like the photon parity. Photon parity had eigenvalue plus or minus 1. So I have a qubit and I learn 1 bit, -1 + 1. But these are unitaries. I can't, it has eigenvalue phases. So this is a lot more information. And that makes this thing harder, because in principle, to determine the eigenvalue of this, I need to get many output bits, right? Okay, so now a little about the error correction. So now you say, well, yeah, okay, nice, but what can this code correct? Now, the way it looks very pretty is that it could correct shift errors. So it can correct displacements. So let's say I have, and this is not very natural, because, you know, normally I have photon loss and all these Kerr nonlinearities and so on. But okay, but let me just assume that I have these types of errors. These are displacements in phase space, and U and V are very small, right? Because the noise rate is not very high. So small excursions, and you can imagine maybe that other errors that have to do small excursions in phase space can be expressed in terms of these small shift errors. That this is some kind of like some basis that you make. But the problem is, of course, that if you have a rotation and you apply it to a state that's far out, it's not a small excursion in phase space. So that's the error model, small errors in phase space. Okay, so now here is a sort of a depiction of these delta peaks, and I've just we've smuggled, because we rescaled Q by a factor of 2 square root of pi to make it sort of simple. But you say, okay, the blue peaks are everywhere where 0 has support, and the green peaks are where 1 has support, even in odd multiples. So the blue peaks, if I go by the stabilizer, you know, those are invariant, right? The state is invariant, so I go from peak to peak, and that doesn't change anything. And the logical X is half of that displacement, so that goes from the green peaks, so all the green peaks gets moved over to the blue peaks. Okay, now what do the errors do in this picture? So you could say, well, around, you know, so there's sort of, if I measure SP and SQ, you know, I have this, well, okay, so this is sort of the region Okay, now I shouldn't say this. Okay, but let's say I have a little error epsilon. Here I have called it U and V. And it's a little shift. So now the idea is now that I measure SP and SQ, or in this case, I measure SQ. And then I try to shift it back, basically. So, the point with the code is that you say, well, code word 0 is here, code word 1 is there. And if I have errors that, keep that there are less than half the distance between them, here it's like physical distance, I can correct it. And here it's also, here's the distance in phase space. So if I have an error that is less than half the shift from the blue peak to the green peak, I can in principle correct it. And the way I could correct this, I say, well, okay, I measure SP, SQ, which doesn't tell me whether I had a 0 or 1, right? Because they're both plus 1 eigenstates. And then I have to do some corrective shift, or I just write this down on a piece of paper. Okay, so, but of course, if the shift is longer, I can't tell, right? If I had a shift epsilon plus logical x, or maybe I have a shift distribution that is very wide, so I can't tell what is. So I get the same information with my measurement if I measure SP, SQ, if the shift is epsilon plus logical x. Why? Because the logical x commutes with SP and Q, so it doesn't change the measurement statistics. Right, so those shifts are sort of bad because they move me closer from 0 to 1 and I won't detect it. Okay, so now one aspect you can ask, like how would I do gates and so on, this has all been developed, but one aspect you can ask about, well, how do I fault tolerant measure whether I have, say, a 0 or a 1, or a plus or a minus? And in principle, this looks very easy. Because you say, well, what I could do, for example, if I look at 0 and 1, and let's say it's destructive. So I just, I'm at the end of my computation, I need to measure all my qubits, and I just measure Q. And measuring Q, if it's closer to an even multiple of this 2 times square root of pi, I call it a 0, and if it's closer to an odd multiple, I call it a 1. That's easy and it's fault tolerant because I don't need to be quite, I don't need to be exactly an even or odd, it's just closer to, right? So if that measurement comes out with some noise, I'm sort of tolerant towards that. I sort of have a region in which I land. Yeah. But this in practice is actually not this has been, I think, a little bit of an issue in some sense. Because the way these GKP states are prepared, not in optics, but in the superconducting, they're prepared in a 3D aluminum cavity or some other cavity, and they are very long lasting there. But you can't do this homodynamic measurement. You can't measure P and Q. The way you can measure it is where you release it from the cavity onto some cable or whatever, and there's going to start losing a lot more photons. And then once it's traveling, you can do these types of measurements. These are very commonly done. But the problem is that you have a lot of photon loss. And the point is that if you measure it, and what they do now is to say, well, we couple it to a qubit, and then we measure, is it a 0 or 1? But remember, that is typically not a fault tolerant measurement, because you're only getting one bit of information. You actually like to measure Q and then say it's closer to even or odd, and then I have some, tolerance towards noise. If I just couple it to qubit and I ask it, it's a 0 and 1, any error in that circuit will mess it up. It's not fault tolerant. Right, so the point is, this sort of GKP sounds like, oh, nice, I have all this, I can measure Q and I have more information, it's analog, people have been pushing this. But in practice, this analog information can also actually be, kind of more complicated. Yeah, okay, well, maybe I'll leave it at that. Maybe you should tell me, because I can go on, but I don't want to, because I think I should just sort of wrap up. Because I'm not going to be able to finish this right now, I think, and it just goes on. So I have a few more things to say about GKP, like approximate GKP code words, what are the things, how we can do gates and so on. I go through that pretty quick, probably tomorrow, and then some experimental data, and then we go to back to the biased noise cats and the dual rail qubits and so on. Yes? Does that sound like a good plan? Okay. Okay. Any questions? Yeah. People are a little bit worn out. Lower the temperature in a fairly effective manner by doing these measurements. And of course, if you're preparing this type of state, you're preparing a pure state, so in some sense it has 0 temperature. Yeah, so the point is, what they do is they say, you know, there's entropy in an oscillator, and what I do is I do a measurement and I get back 1 bit. So 1 bit of entropy is removed, so that should give me sort of a bound, you know, about how much entropy, yeah, I remove, and they say how close are we to sort of that bound. So which is based on encoding the value, yeah. So they imprint the modular variable of the oscillator onto the spin. So they try to read out, you know, that modular variable on the spin. Yeah, but this is for trapped, so this is in the trapped ion, because Holm is a trapped ion person, in a trapped ion setup. Yeah, of course, but you need quite nice control, and we'll go through that. Other questions? No. Okay.
Further questions, let's stand for some.
Yeah.